Ladies and gentlemen, welcome back to the VMware Networking and Security live stream. Boy, that's 2 weeks in a row. We had some interesting microphone and camera issues, browser problems, but hey, we got through it again. We're back here together, and I got Paul Mancuso back here, and we're going to talk about NSX networking part 2. So we're kind of looking for some questions here. We have a couple of things that we want to talk about, but overall, this is going to be a very free-flowing show. We're encouraging people to have questions and to talk to us in real time. So, without further ado, let's bring in Mr. Paul Mancuso, the man of the hour. How you doing?
How are you doing, Andrew? Sorry about making the delay once again. I do not understand, but the desktop is one of those corporate-owned desktops, so I'm certain that there's a security feature someplace that's bugging out on us because it seems to be too often that this is occurring. And we didn't seem to have this issue before, so something must have modified itself.
It's okay. But, just to bring a little bit of a calmer atmosphere to it, I want to let you know that, as I indicated in an internal meeting, I am now a watchman. I own a watch. Thank you very much. It's very weird. It's very weird to wear a watch. Like, I'm still getting used to it. But anyway, I digress. I just wanted to, show in that, I'm now
right,
part of the cool kids.
The time isn't like it's right there.
Yeah, well, I mean, that's true. That's true. I mean, there are some pretty advanced features on the phone. But hey, you know what? This can tell me the weather too. I don't know. All right, anyway,
right.
That's it.
I have the world at a fingertips length away. But if you feel better spending the dollars for that watch and the value that it brings to you, then that's what you should do.
You know what? It's a good thing that we help market and talk about NSX because we are horrible watch salesmen. We are awful at it. So we should focus on what we're really good at. So we'll just focus on that. So, all right. So, you know what, Paul? Last week, we talked about a bunch of topics and, basics of NSX. We went through the history of networking. We talked about, the old school stuff. We talked about, core distribution and access. We talked about a CLOS architecture. We talked about VXLAN. We went through a whole bunch of stuff. So, you know what? I know you have a little bit of an idea, but like I said, we're going to be a little flexible here. What's your idea for today?
Well, I think what we'll do today is let's look at how we provide some of the value that you normally would derive with that VXLAN fabric of the modern day leaf spine architecture and how we're doing it inside of NSX so that we can alleviate the complications of administering some of those servicing. So in other words, we stated that there is a series of infrastructure VLANs that must be constructed inside of the physical environment. And those can be VXLAN backed VLANs so that they can extend pervasively throughout your racks and of course your rows if you so desire within the data center for those handful of VLANs if you find a need to offer them. Because remember, they're going to be kernel element services of the vSphere infrastructure. And we already talked about the fact that technically NSX can do layer 3 management access to the control and management plane of the vSphere host. vSphere obviously can do layer 3 accessing to its host. It doesn't require L2 connectivity to it. But you may want to use things in an L2 nature for some of those kernel functions. And therefore, when you're stringing your clusters across a series of racks, you may wish to utilize a very flat network for those inside of your environment. So for instance, my ACI lab with NSX running on ACI, we use ACI to go ahead and just allow layer 2 to extend throughout the ACI architecture. Now it's a very small architecture. We're only a couple of racks, but at the same point, we do allow it to extend across those 2 racks that are there. So the VXLAN obviously, or I should say the iVXLAN of ACI, since it's proprietary, is providing that extension. But again, it's only for those management services. I have no other VLANs in there except one that I use to emulate a VLAN-backed workload so that I can show bridging and routing to that VLAN-backed workload from within the NSX virtualized network architecture.
Sure. JP is asking a question. He said, where was part 1 of NSX networking? We did it last week. We have it in the YouTube playlist, so feel free to go on back. We have a full playlist of everything. I'll even post it in the chat so that way you can see it. But yeah, it's there. We did it last week, and we're just adding on. If you have further questions, you want us to dive into something, even if we did it last week, we'll do a brief overview of it this week.
Yeah. So if you were to string together a series of racks, right? Let's just say those are separate racks of switching, and you wanted to have L2 pervasively across it, you would normally have to administer that within the VXLAN infrastructure environment in a fairly complex arrangement and array of configuration, combining a series of different protocols. BOM assistance would require possibly some multicast, right? And as you noted, you had that set up inside of your virtualized instances of Nexus switching. I'm not certain that we introduced that to our folks inside of our viewing audience, but Andrew has a whole virtualized array of NXOS switching, just so we can look at how that's emulated as far as managing the VXLAN services inside of an NXOS environment, and compare some of that administration that we would be able to abstract through an NSX software-defined controller-based architecture.
Which is, I think it's important. Like we want to be able to acknowledge that, look, there are, other ways that, Cisco and Arista and the rest of them do VXLAN on the underlay. We're not saying that you need to do away with that. I think that there's a common misconception, and Paul, you can correct me if I'm wrong here, that when people want to adopt NSX and the way that you could do virtualized networking and you can do the distributed security and all these different things, sometimes they feel like, and network administrators feel like they have to throw away what they already have to use NSX. And that's just not true. Now, there are components that we feel like we do much better, much more efficiently, quicker, faster and better. And from an automation standpoint, easier to be able to instantiate. But we're not saying that you have to get rid of what you had there. Paul, what say you?
That's correct. So this is your physical switching, right? So here's your physical switching. And to extend L2, normally you would have to configure the VXLAN environment to map the VNI to the VLAN to a VNI, and then extend that as an L2 bridge segment throughout the infrastructure itself. And then, of course, you could utilize that bridge segment for a multitude of different VNIs, so that if you wanted to, you could use that single VNI value and map a series of VLANs to it throughout your environment. But the idea is that you still have this fairly complex arrangement in order to correlate that configuration throughout your environment. And we're going to show you that we don't have to do any of that in order to administer the connectivity of our world.
Makes sense.
When we craft an NSX environment and we utilize a transport zone, in that transport zone, we'll utilize it with this purple line here. So this will be our NSX environment in here, right? Wow, that screech sounds beautiful.
That was a good squeak. I like that.
Okay, so this would be our NSX, and it's embedded in the hypervisor. So when we talk about things that are inherent, that's what we mean by inherent, in essence, because we're not layering on something, we're essentially layering it in something. So it's a big distinction, because it doesn't add any type of overhead to the extent that layering on versus layering in would imply. Layering in essence, allows us to operationalize the networking and security services of NSX in an inherent fashion, so that when you create that distributed switch, it is NSX. NSX and the distributed switch are one, and they become the same, so that we can have logical segments and we can have VLAN back segments all on that distributed switch. And then wherever we state the clusters of NSX is present, in other words, which vSphere clusters, we utilize through the virtual machine management of NSX Manager to add in vSphere or ESXi clusters into the NSX managed environment. All of those immediately get embedded with the NSX virtual installable or VMware installable bundles, which therefore allow them to begin participating as soon as we make them transport host. So we have to make them transport host inside of NSX. So we instill the NSX goodness, and then in order to get them to provide networking, we have to manage them through NSX Manager. And so maybe we could start bringing some of this up, so this becomes to we map the abstracted discussion here on our light board to the reality of an actual lab environment. So Andrew, I think you said you had one, right?
I do. And let's highlight one of the things there. So, what I think is one of the more powerful things that we have with NSX is, you were saying, you install the VIBs and, you add that into a host, and you add that as a transport node. you're automatically expanding not only from the networking capacity, but also the switching capacity, the security capacity. You're adding into the NSX fabric, whereas if you were going to have to do that on the physical layer, you're having to add in, physical switches, physical routers, physical load balancers, and things. You're having to then, put all these different specialized components, configure them and interconnect them in some way, shape, or form with speeds and feeds. Whereas we're just utilizing the host, and the host is really what's providing the power and creating that virtualized network fabric. So yes, I do have a lab here, Paul. Is there something specific that you would like me to show in the lab?
Well, I was going to say that we add in these clusters across the environment itself. And then when we start talking about, let's actually just draw in, I guess, another one here.
Sure.
These boxes always got pretty little lights on them, right? All right. And then we draw in, let's say, the logical segments that we're going to talk about, so that within NSX, we have these logical network segments, so that we state that we can host workloads on them. And this would become an L2 segment. So here's an L2 segment inside of it. And then we can provide distributed routing. So when we talk about adding in distributed routing, it just means that in every one of these hosts, there's a distributed network. Okay. I've never drawn it this way. I just thought I'd try a different paradigm just to see how this works out. This distributed routing component that's embedded in the kernel, so that every one of these L2 segments is routed on an east-west basis within our virtual network environment, so that the only thing that the physical infrastructure sees is the communication coming from the tunneled endpoints. They don't see the actual original Ethernet packet. That frame is embedded inside of another frame. So this overlay that we provide inside of the virtual network of NSX is then transferred into the physical fabric as an encapsulated frame with an Ethernet header that is essentially the source of the original TEP that's coming from the host. And the destination MAC would be any gateway that's required in order to get to the next TEP, or maybe the TEP itself if the TEPs are all on the same L2 plane. But the actual Ethernet frame that's encapsulated in our Geneve encapsulated tunnel is actually embedded in the data service portion of that of the original frame.
I think you hit a very key word there. So let's focus in on a key word there. You said tunnel endpoint, or that TEP. So tell me, Paul, how does the TEP relate to the transport zone that you have there in purple?
All right. Well, then if we were to speak to the TEP itself, so that we have, let's say, a distributed router. Well, in each one of these things, there's technically a TEP as well. So we could say that this is a TEP, and I don't want to have to draw it for each one of the hosts because they're obviously utilizing an individual one for each of these. So each of these systems that interact, they'll each have these kernel elements. They'll have the vSphere distributed switch. The vSphere distributed switch will have, for the purposes of NSX, the management and vSAN and vMotion, et cetera. Those kernel elements may or may not exist. Obviously, management must exist. But the kernel functions of the tunneled endpoint system will provide the interconnectivity of the NSX virtualized network. And that's essentially what we refer to as that transport zone. That transport zone creates this network of continuity between all of the vSphere clusters that we associate to the transport zone. And then inside of NSX Manager, we go ahead and say that they're transport nodes, and then through a series of abstractions to provide how that is interacted with the ESXi host. In other words, we need to tell it which of the physical NICs that are going to become the virtualized infrastructure representations of how that TEP is going to communicate through the VDS and into the physical infrastructure. And of course, we have to state whether or not it's going to use whatever vSphere algorithms it's going to use, whether it's a lag or whether it's going to go ahead and utilize route based on source ID, et cetera. And then that TEP interacts with the distributed virtual port group of the VM kernel services for that TEP. And then anything that is sent from a host hosting workloads on any logical segment that we have created inside of our virtual network will now utilize one of two basic communication pathways. If it's a switched or routed communication within the host itself, well, the actual transport network of the environment that we have been creating and discussing doesn't actually ever see it, because it just gets transacted in the backplane of the host itself. So it gets switched or routed. But if it has to go to the physical network, it's going to go through that tunneled endpoint of the kernel, which is going to encapsulate the original Ethernet frame, put on another Ethernet frame header, and go ahead and then pass it out. And of course, its destination will be what I've said before, one of two things: either a gateway MAC of because the TEP that it's going to as a destination is on another layer 3 network of the physical environment, right? The underlay, or it's on the same L2 plane. So the MAC address will actually, in the Ethernet frame, will be the destination TEP itself, and the source and destination IP will reference the source and destination TEPs.
So sounds like a lot of normal networking, just traditional kind of style of encapsulation, overlay networking, all that stuff, the normal stuff that we've seen in networking every day. And we're doing the same thing here. Now, I do have a question, and, nice pop quiz for you, and I'm sure you're going to know the answer. What if I had two different transport zones and I had TEPs in each one? Will they be able to talk to each other?
They would not speak through the transport zone itself. What would have to happen is we would have to route them from the layer 3 of one transport zone to the layer 3 of the other transport zone. So we don't support a multitude of transport zones inside of an NSX deployment, correct? You would have to have that routed. Is that a question that came up from someone in our audience? Or
no, I wanted to point that out because that's by design. That is something that we do. That is a way of being able to separate out TEPs. If you want to, you can have that layer separation by creating separate overlay transport zones and then having them, attached. Let's say you had like a PCI zone or whatever. Typically, we don't see that, but we just wanted to show that there is, logic in how essentially TEPs are associated with the transport zones. And not to say that it can't happen. We can do some fun things in routing and switching, but it isn't inherently allowing a TEP from one zone to be able to reach a TEP from another zone.
Correct. So when we speak about the use of these tunneling endpoints, so that's what essentially this is here. So let's go ahead and actually mark that. So this would be the tunneling endpoints themselves. Oops. All right. The extent of communication will be wherever we have that singular transport zone, so that encapsulated traffic passes between an east-west basis, almost like a leaf spine architecture of the physical, but from a virtual perspective, so that communication from one logical segment, in case we had more than one up here. So if we have another logical segment, so this would be another one. So this would be, logical segment, let's say 2. This is logical segment 1. Let's say any virtual element on this particular segment communicating to a logic or to a virtual workload on this segment would get routed through the distributed router on the source machine. And then the packet that's actually encapsulated and sent is already routed from a perspective of the environment. It still, of course, has the original Ethernet frame of this virtual machine. So the distinction and difference is actually going to be the source and destination MAC address of the Ethernet frame that's encapsulated. The Ethernet frame that's encapsulated is going to look as if it's already routed into this other segment, and it's already resolved the endpoint of that system itself in the encapsulated portion. And the TEPS is simply saying, I know this virtual machine's MAC is on this TEP. So therefore, the encapsulated frame is going to essentially say, I need to send it from this TEP to this TEP because that's where this virtual workload is hosted. Because the MAC address of the destination system has been resolved through our control plane in NSX, and it is now shown inside of a control plane table inside of NSX controllers that this particular host in such and such rack has this virtual workload. So therefore, the routing actually occurred on the source machine at the encapsulated packet. The outer frame is still going to say this TEP to that TEP as source and destination. The inner frame is going to show the fact that this workload from an IP source and destination to this one. But again, like I said, the destination MAC will essentially be this virtual machine. The source MAC will be the distributed router source MAC value.
So a question that came up from Thomas that's watching from France. Hello, Thomas from France. You said, where is the MAC and TEP address table located? That's what I believe he's asking there.
Well, the MAC address table is kept essentially, we have a centralized set of controllers. So we talk about NSX management, recognize the fact that we have a centralized control plane that provides a proactive administration of information of where workloads are discovered and populated within the infrastructure itself. So when a virtual workload loads up, remember the vSphere infrastructure, it would do this. Let's just wipe out NSX for the moment. NSX doesn't exist. When this workload comes up, the virtual machine actually shows up in vCenter as being hosted on a virtual, or excuse me, on an ESXi host, on a distributed virtual port group, and all of the information is exposed due to the fact that the vSphere environment immediately knows where that workload exist inside of the virtual infrastructure. Well, NSX does in a way the same. It actually then sees the fact that this particular workload has its IP and MAC value and associates the MAC value to a TEP based upon its discovery after its boot up, after its boot sequence. So it pulls that MAC value, it sticks it inside of the NSX control plane information, and now it is aware of it so that anytime a workload, anytime another system is attempting to communicate to it, the NSX environment can proactively communicate the knowledge of where that workload exists in the TEPs, because the TEP tables get automatically updated with that knowledge. So therefore, all of the TEPs are aware of the other workloads simply upon the boot up sequence of your virtual machines.
So I think that's important to say. So all of the hosts that are NSX enabled and have the fabric, they are aware of the MAC addresses of the hosts that, or I'm sorry, the VMs that are living on them, and are also aware of how to be able to reach other TEPs and other VMs on other hosts.
Correct.
No problem, Tomas. Sorry, just go ahead. Go ahead.
No, he said thank you. So
yeah, he said thank you. Yeah, I was just saying, no problem whatsoever.
Okay. This means whenever a TEP is trying to communicate to something, it obviously looks at its table. Now, if its table has somehow lost track of that other distributed or other virtual machine, we have a system inside of using BUM assistance from a NSX perspective to discover where that workload persists inside of the environment, where we can use head-end replication to actually find it, or a multicast replication in order to discover it across the entire plane of the NSX TEP environment. But nevertheless, it's a little more complex than we need to get into. But the idea being is that we have an automated means of finding it in an out-of-band manner, so that we're not using the traditional Ethernet mechanics to get to it, obviously, because we're simply using NSX control plane to automate the locality of that destination workload, and then of course instantiate it, not only the MAC to the TEP, but obviously any information that's required in order to craft that packet so that we can go ahead and send that packet in a complete nature to the destination.
Real quick, just for our non-networking people, you said a key term there, BUM. What does BUM stand for everyone?
Broadcast, unknown unicast, and multicast traffic. So
Perfect.
Broadcast in this sense would be the necessity possibly to send out a series of queries across a plane of communication in normal Ethernet speak and parlance to find something. But in this case here, obviously we're referring to the way NSX is going to go ahead and communicate that information. And NSX, like I said, has a few different methods of setting it up, but the default is just to use the head-end replication in order to discover. So it just sends out a query to all of the other hosts that it knows of within that transport zone to discover the workload by querying whether or not this particular destination IP exists inside of its environment.
So I think, we went through a lot of information there. So let me go ahead and do a little bit of recapping here. So we had our transport zone, which essentially TEPs can be associated with in some way, shape, or form when we prepare our transport nodes. They can then thereby have a visibility or accessibility into the other TEPs on other hosts so they can communicate with each other, transfer information, transfer packets between a virtual machine that's living on one host going to another host, and uses Geneva encapsulation to be able to bring that over. Pretty cool there. Last week we talked about our tier zeros and our tier ones and how those things interact. We talked about segments and how they connect into that. We went through a lot of different things there. We even talked about edges and how this thing is distributed across. So just putting the pieces together, that while it sounds complicated, what we're doing here is just breaking down every singular part and how they all interact with each other. And the key thing to know is all this configuration was done with an NSX without any kind of special configuration that needed to be done at the physical layer, at the physical switch. You notice that Paul didn't touch anything there on that lower level. To us, it's just a connectivity mechanism. It's just a way to be able to send packets out, but we didn't have to be concerned. As long as the TEPs have connectivity to each other, things just happen.
Right. So in other words, this environment, this TEP environment, let's just say these were L3 connected. So this would be like a 10.1 0.0, let's say /24 network. This one would be a 10.1.2, okay, .0. All right,
Sure.
/24 network. Okay, and this would be another TEP of 10.1.3.0/24 network. So it's obviously horrible.
It's just highlighting the fact that it could be whatever it wants to be.
That is correct. So these are routed to communicate to each other. Therefore, we don't have to extend them inside of our underlay environment. We can just set up a normal L3 routed infrastructure in here so that these can communicate through either OSPF or BGP and utilize a very simple routed connectivity, and don't have to use any of the extraordinary mechanics that you may have to utilize in order to extend these communications of, let's say I want to communicate on another virtual workload, let's say on the same L2 plane as, let's say this is VM1 and this is VM2 and this will be VM3 over here. These are communicating on the same logical segment, yet the TEPs are going to have to route in order to get this communication from VM1 to VM2. The TEPs will route to another, but the Ethernet packet that is encapsulated by that tunneled communication will actually show that it's L2 communication using an L3 routed segment in order to attain access to that destination virtual workload.
And yet again, Paul,
explicit here. We just use normal.
That's
IP.
the thing. It's normal IP connectivity. And yet again, like we said, we talked about the history yesterday, or not yesterday, but last week in that part 1 episode, where we went through core distribution access, that traditional style that was there, and then a CLOS. But in this situation, we don't care what it is. Like, we don't care how that underlay is built.
No, and the underlay, in essence, should be as simple as possible so that if there was a communication issue, a flow between these two workloads, obviously we'd look at if there's a historical sense of that they ever communicated, et cetera, and you go through your normal means of trying to scope and discover the source of the problem and scope it to a specific set of issues or issue itself so that you can then discern where the problem would. So if there was a historical communication between them, obviously something must have changed in order for them to no longer communicate. If it's obviously rack that you've just run up and nothing in that rack is communicating, obviously, yeah, you're testing out something that you've just deployed and you ran a test workload up and communication to it could not exist. So now you're going to go back and look at probably a configuration issue on that newly set up host with hosted resource or hosted workloads in it.
I think what's also important to note here is, like, look, we talked about Geneve encapsulation here, and we were talking about the communication between the TEPs, and we were talking about how the control plane works and how it was keeping track of the MAC to IP address or the TEP address table. What's important to note here is we didn't talk about in the physical layer setting up multicast. We didn't talk about in the physical layer setting up multi-protocol BGP with EVPN. We didn't talk about setting up VXLAN TEPs. We didn't have to talk about doing any of that stuff. We didn't have to talk about how to do a BGP control plane and be able to pass that information between all the different hosts in the physical, or I'm sorry, the switches in the physical layer. None of that was needed to be done. Not saying that it can't be done and presented as connectivity to NSX for that TEP connectivity. It could all be done. But from our standpoint, we were able to do all this stuff by simply installing NSX and making sure that the TEPs were reachable on a layer 3 fabric.
And that's the whole point of this. This isn't really meant to go through a whole troubleshooting workflow to discover how the communication pathways gets discovered by each of the various TEPs inside of the host and how they communicate through the management plane back to the NSX controllers in order for them to pull down endpoint resolution information if they don't have it persisted in a cached in their cached values on their own TEPs themselves. The idea here is to look at what is the simplicity NSX is abstracting away from the physical fabric by running the services as we do so that when we talk about L2 communication on the same VNI or L3 communication between two VNIs, we don't have to concern ourselves with the traditional VNI, VXLAN in Fabric with utilizing integrated routing and bridging and determining which L2 bridged VNI is providing this VRF connection through this connection, et cetera. And then like he stated, which control plane protocol is actually providing the resolution of information for the source and destination of the workloads. All of this is abstracted away by the NSX control plane itself. And it's a very simplified control plane where you really only have a handful of elements that are at play and at work here. It's the NSX controllers, which are essentially a service of the NSX management virtual appliances that you deploy because they're one of three different services: your management, your control plane, and security policy manager of the NSX managers. Those are your elements that are inside of that virtual appliance that you're deploying and utilizing, consuming compute and memory overhead of those virtual appliances. And those are actually the center of authority for endpoint resolution. So the management obviously configures the environment itself. The control plane maintains an understanding of how to provide that endpoint resolution and what services are going to be rendered by the NSX controllers in order to either proactively assist or react to something that is asked of it out of band. So that if, for instance, a TEP is looking for a workload, it doesn't know where it's at, it sends through the NSX management connection to the NSX managers to get to that controller and say, listen, I need to know who this virtual machine is and where is it located at, and that it gets a response back. And at that point, then it can craft a frame from its TEP to send to the destination TEP. And then that TEP, of course, will unravel the packet and deliver it to the endpoint. Now, it's a little bit oversimplified, but that's essentially the gist of it. And when you get it from that perspective, I didn't oversimplify to the point where I had to talk about a conglomeration of different protocols that must work in concert together in order to provide the BUM assistance and then the EVPN knowledge of the overlay connectivity and which VNI is this being manipulated and managed on the bridge or a routed connection between one VNI between another. These are differences in the perspective of how we provide our servicing and how we can troubleshoot it in a much more rapid fashion. So in essence, because we're completely virtualized, completely abstracted, and we don't have this control plane buried and burrowed into a physical ASIC appliance that has some specific limitations as far as its capacity and how it must calculate or how it must be able to attain and maintain that cached information for its environment, we can do so in the virtual infrastructure in a far easier and much more elastic manner. We're not we're not imbued in by the way the physical infrastructure is constructed in order for workloads to be interacted with from a switched or from a routed perspective. We act completely agnostic to it. We just need the physical layer switch to tell how to get from this TEP to that TEP. And the few thousand workloads that might be at play there are essentially taken care of all by the NSX abstracted world, or the workloads are all taken care of by the NSX abstracted world, making this far easier to manage, manipulate, and to interact with, and to scale and deploy additional workloads. One of the things that we're going to talk about, not today, but we'll get to at a later time, is that VPC construct. And you're going to see that because of the simplicity of architecture, we've been able to add a really cool feature so that you can now utilize a self-consumption model for deployment. And self-consumption just means that I can have the app dev teams go ahead and just begin consuming NSX without having a SME tell them, well, here's your security group and here's your logical segment, and this is how you need to route it, and you need to tell me if it's connected and if I have to filter this into the routing protocol or do I need to unfilter it. We're just going to set up a world where there's a base set of elements, and the app dev person is just going to go in and say, you know what, I need an IP address, so let me take this segment, let me go ahead and deploy it inside of these groups, and voila, they'll have transparent, interconnected, and secure servicing of those workloads. All of that, I mean, is based upon the base elements of what we're discussing here today, though.
Just the base, yeah, I know, and it builds upon it. Now, just to show, like, you know, Paul, you had a wonderful way of summarizing all that. You know, let's talk about, and I just brought up in, you know, my lab here. I brought up this situation. So we were talking about the very famous lab that I have. So, I mean, we were talking about, you know, the encapsulation, the TEPs and things. You know, look, even if BGP was already set up, multi-protocol BGP, we had EVPN working, we had everything going on. If we want to add in, you were talking about, okay, we got to create a VLAN, we got to associate the VNI, we got to then associate to the TEP. We have to do all this configuration. We have to do a lot of stuff that is involved there to be able to make that happen on the underlay, and then put that into all the different switches that are going to participate in that, and make sure that everything's going across on, you know, multi-protocol BGP, depending on if we're using multicast to be able to learn for bum traffic. But look at how simple it is that if I just want to go in here in NSX and just go, all right, well, new segment, and I'm just going to go ahead, put it on the tier 0 there, and I'm just going to do an overlay, and I'm going to make it a 192.168.10.1/24 and do that, and then I hit save. That was it. That is how quick I made a layer 2 segment in NSX versus having to go through all of these different components and all these different physical devices. Not to say that you can't do it. We're not telling you that you can't, but we're showing the incredible simplicity that is involved with doing it just right there with a few clicks of a button. And I'm not even talking doing it. I can do this through an API as well. I can send a singular call that has the JSON payload, has everything there, boom, done in one click. Instead of you saw me do it, I think 3 clicks, and you know, I typed in something real quickly. That was it.
Right. Like, not to mention, that logical segment you created has the capacity to hold multiple thousands of workloads. It has the ability to enable distributed firewall services in the inherent capacity of its nature. In other words, when I say of its nature, I just have to start writing firewall rules inside of the NSX firewall, distributed firewall a portion of that platform of our dashboard, and immediately rules will get enacted upon those workloads so that the communication now can be assured that it is only between those two systems over a series of different ports that I designate.
Yeah, and I think that's the important thing also to talk about there is, like, you know, you have the ability to, you know, do multiple things here. You can create a traditional 3-tier architecture if you wanted to. You can do a segment for web, a segment for app, a segment for database. You can use the gateway firewall to be able to prevent connectivity between them. You can get down to the microservicing layer, and you can, you know, write out, different policies between them, or you can have it on one large segment if you wanted to. You can just create a brand brand, just a big segment that puts all them on there. And it still doesn't have that, like in that traditional networking world where you have things on the same layer too. Now we have to start talking about potential, private VLANs. We have to start talking about some complex things there, as opposed to I can just inherently do microsegmentation directly on that VM without having to separate a layer 3 boundary and forcing traffic to some type of device to then finally do policy management.
Well, and so where's the operational reduction come from then? Because obviously we are managing a network. Well, you have the simplicity of what Andrew just showed you to create a segment that now extends throughout the transport zone. So wherever that transport zone has been designated by the environment, and by the way, we can talk about scaling in a moment, that L2 segment persists. So if I add another host, another cluster of hosts to that transport zone, that segment or segments of that entire transport zone gets mapped over into that host or cluster of hosts, so that I don't have to do anything extraordinary in order to provide that scale. I simply add to my infrastructure environment what is a necessity. So I get additional networking, and of course I'll get everything that rides along with what runs inside of NSX and whatever you have licensed. So by its nature, distributed firewalling would be available to you if you had networking already as well. So you would then have that DFW servicing that would then get extended into those new hosts. So that's the simplicity. That's the elasticity. That was that idea that I said that we're not bound by the physical realm. Obviously, we're bound by the fact that the ESXi clusters and our transport zone must communicate to a physical switch set of TORs that must obviously interact and communicate within the site and between sites on our behalf. But my point being is I'm not bound by any of the abstracted configuration elements of that physical infrastructure. As long as these two switches are aware of how to interact and communicate to the other switch at the other end of the data center, I don't care. I can go ahead and craft my solution and never touch that physical infrastructure.
And Paul, you know what? Let's do that again in real time here. So let's just have some fun. So I actually just right now, Paul, have a tier 0. I actually use this one for my VPC demonstrations, but right now we're just gonna, hey, so you know what, Paul, what we're gonna do is we're gonna create a brand new tier 1 router here. So we're just gonna call it, tier 1 router, and I'm gonna go ahead and link it to the tier 0 and create an edge cluster. Now notice I don't gotta set up BGP. I'm not doing BGP here. I'm not setting up anything from a tier 1 to a tier 0. I don't have to set up IP addressing. I don't have to do any of that. I'm just going to create a tier 1 right now. That's done. And then let's say that I'm going to migrate some application here. I'm just going to simply call it, a web, one, and it's an overlay transport, and we're just going to do the 192.168.10.1/24 and create that web segment. We're going to go ahead and now create another segment here. So that's done there. We're going to create that app segment. It needs to be done all of a sudden. And, this is Friday, at 11 at 4:50. And I want to be able to get home because I got some stuff going on here. Like I want to meet up some friends and have a good time and, have a couple ginger ales. So I got to quickly create this stuff right here. And I'm doing this while I'm talking to you, Paul. I'm not even having to really think about, besides my addressing schema here, which I probably already pre-planned out. And boom, look at that. I already created everything there. It just while I'm talking to you and just like talking about I'm going to have some ginger ales with some friends and I'm done. I didn't have to go in and do all this complex configuration on the underlay. It's just done. And then from here, when I want to go in, I can go in and start creating distributed firewall rules based on that information. I can do all kinds of matching with it. I can do all kinds of grouping and dynamic learning, all that stuff. I did that within 30 seconds. I did that while talking to you.
Right. So what he essentially did is he stated he created a T1. He created a couple of segments so that they would route between themselves. So what must have already existed if we wanted these to communicate externally? So what you must have already had is a T0.
I sure did.
So you had to have a T0. And so where did that actually exist at? Well, that existed as a series of another cluster that we're going to refer to as our edge. All right. And this tier 0 inside of it would be our edge cluster. So that edge cluster is hosting these T0 instances, all right, inside of them. And we'll talk a little bit later on. I think today we're not going to get into it, but the T1 obviously also has to have its instances as well. But nevertheless, the T0 instances would be hosted inside of this edge environment. And when you created your physical infrastructure, what did you do? You deployed the physical switches, you cabled them all up, obviously, okay, et cetera. And then you had to create some type of modest underlay communication, whether it's going to be that layer 3 routed or that VXLAN minimal back, or that VXLAN environment with a minimal set of VLANs that are mapped into the VNI, so that you can go ahead and provide L2 continuity, or you could just use a layer 3 as we're showing here with our TEP, so that each of the racks essentially is just going to go ahead and route the services between the racks, so that only the racks have L2 continuity from a physical perspective, L3 between the racks. And therefore, that would be our base setup. Well, for an NSX base setup, we said this in an earlier video, that we have to deploy our NSX managers. We'd have to instill the VIBs that we wanted to, or the inside of the ESXi clusters that we wanted to provide uses of as transport nodes. We had to discern which of our ESXi hosts we're going to play as our edge, so that we can offload our virtual network environment and de-encapsulate it, and then bring it back into the VLAN-backed world of our physical environment, so that when workloads are coming into the virtual infrastructure, they're essentially going to ingress through that edge, and they're going to egress through that edge, right? And when they ingress, they're going to get encapsulated, and they're going to ping pong back and forth through the TEPs that we just discussed at the beginning of this particular video. And then when they leave this environment, the TEPs themselves are going to send it to an edge, and then the edge is going to go ahead and de-encapsulate the frame and send out the original VLAN-backed frame into the physical infrastructure. And the edge itself, of course, will be aware of how to communicate that to a destination based upon routing of the IP domain that we have permitted to be known to the physical infrastructure of the virtual infrastructure. Because remember, we might have a series of prefixes here that we want to go ahead and advertise through that edge, so that the physical infrastructure is going to communicate directly to the virtual machine's known IP address, or we may NAT that information to the physical infrastructure, and therefore we're going to have some NAT services on that edge, obviously, where we're going to either NAT it off of the T1 or the T0. We can talk later on how we can do that service-oriented feature within the virtualized infrastructure and NAT that information to the physical infrastructure, so that the IP addresses here are of a private source to the virtual infrastructure. Now, whether or not they're obviously using the private IP domain space, as from a smart perspective, but the idea being is that they themselves, that IP address is just known only to that virtual environment itself. It could be VPC oriented of NSX itself, or it just could be a regular logical segment that's not oriented inside of some tenant architecture, but we strictly don't want it to be advertised externally. So when the T1 here is actually routing to and from it, it's obviously providing it, or the T0 is obviously offering a NATed service.
So I like to always look at explaining the edge as it's the main on-ramp and the off-ramp into the NSX fabric in some way, shape, or form. That's where we're going to have our BGP. That's where we're going to have our connectivity to the underlay network. That is really how we're getting to the enterprise network into the NSX network, in and out. You can be most simply, if it was a stub network of some sort, you can simply take a default route into it, and then we can advertise the routes that are known, so that way the enterprise network knows how to be able to get into the NSX fabric to get to all of these segments that you're going to create. As Paul stated, we can also use NATing and all these typical normal things that we have in networking. So all these normal concepts that we have in networking, we're not reinventing the wheel. It's all the same, and what we're enabling is a quick way of operationally being able to scale out this infrastructure by growing the cluster, by deploying more hosts with the NSX VIBs, by expanding your edge clusters with more VM edges or even bare metal edges. All these different things can happen, and we make your life so much simpler, because running a data center is really, really hard.
Right. And this T0 edge, although it looks like a little comical cartoon character at the moment, the way I drew it, that also has a TEP. And it also has a distributed routing element that we're embedding into it. That's that T0, but it's obviously got a special type of service that's going to allow it to communicate to the physical fabric. And we'll talk a little bit more about that later on. It's a service router service that will be utilized so that it can communicate to the physical infrastructure. And as we noted, if it had NAT, for instance, that'd be another SR service that we align to it so that it would also provide the NATing for DNAT and SNAT. So when providing the setup of our edge, that's what we have to do our planning. That's where our planning in NSX really takes hold. It's not that we didn't plan to obviously add additional segments, but the idea is that we planned ahead of time how we would like the perception of this virtual network environment to be perceived to the physical infrastructure, whether the IP domains would be known and advertised, whether they would be NATed, or whether there would be the concept that we're going to NAT some and we're going to advertise some, but we plan what that's going to look like so that we can scale it appropriately at our edge, because we can't just sit here and willy-nilly and set it up. We obviously have to have a design plan, because a good design should not require a reconstruction at some later point due to a faux pas in understanding what will come down the road. We should make certain that we have the ability to scale our needs to the future and the ability to set up all of the services that we wish to consume at some point in the future, even if we're not using them at the point of initiation. So those are all the things that go into a grid design at the beginning. And that's the part that takes a little bit of time. So although we say it's only a few hours to set up the base elements of an NSX infrastructure, the management, the transport nodes for the edge, and the edge clustering itself for the T0 off ramping of our infrastructure. And then it took Andrew less than 38 seconds to craft 2 segments in a T1 that communicated externally and between itself. It probably took, obviously, a handful of weeks, if not a little bit more, in order to make certain that I had an appropriate designed environment before we engaged the deployment of NSX in that environment. That's just a normal thing. So I don't want anybody thinking that, oh, it's just seconds to set up your NSX world and there isn't some base design obviously built behind it. That's obviously nonsense.
If I would have had to do that in the old school days in a data center, you know how many change controls, Paul, I would have had to submit?
Right. But knowing that, what we are removing then from the physical infrastructure is the fact that we now look at what are we designing for? We're designing more for capacity. What IP addresses that we will have to make certain that we're going to allow into the NSX environment. So obviously you have to segment your IP domain space to make certain that you're aware of what IPs will be advertised, what IPs will be known, and what IPs will not be known into the physical. So, there's a handful of, I don't want to go through all of them because obviously the list would be a bit long, but it would be much shorter than a normal infrastructure that would have to be for the physical, because the physical infrastructure here is going to stay fairly stable. There's going to be rarely little dynamic aspects that will play into it from a day-to-day basis. Obviously, if we add a new service that we planned inside of the virtual infrastructure, there may be a bit of modification and change that will have to take place at that edge. And of course, make certain that that IP address information is obviously going to be allowed and communicated appropriately into and out of our NSX world. Those kinds of things, of course, will take place. But what I will not be doing is, when I crafted those workloads, literally have to do nothing in the physical infrastructure to make that happen.
We have a very long question here, so let me see if I read this right. Is it possible now to have a sort of local egress preference on multi-site? I see vSAN stretched. I might have a question there. How to be sure to pin VM site A to edge node or edge subcluster site A in order to avoid east-west traffic?
Well, with multi-site, we're going to have a problem because it depends on if you wanted active-active or active-passive. And you're going to have an issue on how that operates, because we can't pin it to a local egress as we could with NSXV with NSX multi-site. So you mentioned multi-site, so you may not have actually implied the idea of what NSX or VMware would state is an NSX multi-site. NSX multi-site is an actual design, an actual manner of design of NSX, taking a single NSX instance and wrapping it across 2 or more sites. That would be NSX multi-site. NSX federated or NSX global managed with NSX Plus now, we would have separate NSX instances at a bare minimum at each site. There could be more than one instance at each site, but we'd have at least a separate instance at each site globally managed. And even then, local egress in itself on an active or an active standby for that segment, that actual segment itself, would make for an interesting use case discussion that we're not going to be able to answer in just a simple question as the way it's drawn here, because we would have to know how are you wanting to extend it? Where did you want the ingress to come in? And where did you want the egress to come out? That all would make a difference in how you would then manage your edges in such an environment. And obviously, like I said, is it multi-site or is it NSX federated or NSX global management?
And to add on to that, Paul, so we actually had a show where we talked about multi-site, and it was the first 39 pages of this guide that I'm actually going to be sharing on the YouTube and also on the Twitch chat. It's a wonderful NSX multi-location design guide. It talks about federation. It talks about disaster recovery. It talks about multi-site. Like I said, Paul and I have touched upon that. There's a few different design considerations and a little bit of language and syntactical differences, if you will, of like what multi-site versus a multi-location versus a federation versus all those things. So Thomas, I very much encourage you to take a look at that document.
And I was going to tell him, I didn't want to interrupt your train of thought there. I was just going to add at the end, whenever you were to complete that, that will be our next discussion. We will do the remaining balance of that multi-site discussion. I think as we hopped into doing that, because that was just something requested initially. So we thought, let's just do that first. And then it made little sense, since we were hopping into such an advanced topic, not go back and cover some of the basic elements like the physical infrastructure itself, how logical segments and distributed routing actually occurs in a much more meaningful manner than that limited way we did one of our discussions. So we thought we'd do a more fulfilling manner of discussing all of that, so that there'd be essentially a base set of understanding built into the environment. Therefore, then you could go back and watch that first one, make sure you're aware of how you're setting up a site, and then we're going to talk about multi-site, and then we're also going to then go look at multi-site disaster recovery, so that you can start to understand how you're going to provide the answer to that one that was just given, at least if it's an NSX multi-site topology.
You got it. So great question, Thomas. I appreciate it. So Paul, we have reached, we're almost at the hour. So, we kind of rock and rolled here. We went through part one, just to recap, we went through a lot of the history of networking and like how we got here, if you will. And then today we really dove in on NSX centric networking and how it was different from making a VXLAN centric network or using legacy architectures like core distribution access. We've now talked about from an NSX standpoint, the simplicity going into it in a live demonstration and creating some segments, some tiers. We talked about the edges. We talked about transport zones, transport nodes. Holy cow, we went through so much in 57 minutes. I can't believe we got through all of that, but we did. We want to thank everyone for those questions. And Paul, any closing thoughts before I wrap the show up?
I think it would be interesting to go back and at least give a simple explanation to the gentleman that posed a question in our last one that we didn't offer him information to. But you essentially wanted to know something about why did I have to set up a specific NFV function in order to provide route target mode of an L2 communication. And it's because what he was probably attempting to do wasn't really meant to be used by that topology arrangement that VMware has provided through NSX. That was explicitly set up in that particular arrangement to solve a telco problem that had to use that NFV function in order to provide that L2 communication through that L2 communication in a route server mode, I believe, right?
It was using route server mode and type 2 connectivity, essentially for the layer 2 extension of the MAC address and IP. Right. And we actually had a discussion with the people involved, and yes, it was for a specific use case in the telco world.
Which is what I asked the guy. Remember, if you recall, if you go back, probably about 20 seconds after you had read it, I kept saying, I bet if this is for a telco issue, I know there's an explicit reason that was set up. If you're using it for something else, then I'll have to check. And that was what I was asking. I wanted to go back in and ask, because I kept thinking of, you're right, we don't really have a solution yet specifically for what he was probably asking. But that isn't something we're required to do. That is something we did to solve a telco problem. And we'll be offering some enhancements to the way we're providing EVPN management of traffic communication as we move forward, as we add in new service capability into NSX, so that we can solve that problem without having to do that. Assuming you're not talking about a specific explicit telco problem, we are solving, it is required to use that solution.
He's actually here. He says, yes, it was from a telco article. And absolutely. And actually what we would do is that we actually had a request back to you. So if you do have a specific use case and why you want to do this, our product team actually was very interested in knowing more about this. So what we encourage you to do is, if you do have an account exec or a systems engineer that you're working with at VMware, please reach out to them and let them know that you want to talk to. You can directly reference us, Andrew and Paul, and you have this live stream of what we're talking about. We want to hear from you. We actually want to have a direct discussion with you and your team. So if you would be interested in talking to us, please do reach out to us. Have your account team reach out to us, and we want to have a more in-depth discussion about this and your use case.
Well, Andrew, that's it for me then. I definitely am zonked out. I've given too long sermons today, and I do mean today.
You did. I know you.
That crossed the time zone of yesterday and today, and then I did another one of that earlier today. So I am definitely a bit wiped as far as energy, but I wanted to do this because, like you said, you had set this up. So I tried my best, though, to obfuscate it with a bunch of issues on my end with the browser.
No worries. No worries. It was fun. I mean, look, you were a champ. Last week you did the stream on your birthday, and now you're coming back from what seems like an extendedly long day from yesterday and doing this again. You didn't get to sleep till like 3 a.m. So I'm going to wrap this show up. Give me a second, Paul. I'll be right back to talk to you. Just give me a minute. Ladies and gentlemen, thank you so much for joining the VMware Networking and Security live stream. We're going to have more of these. Obviously, we have the networking side. We talk about the security side. We talked about VPCs, and that's a coming show. Multi-site, disaster recovery, all of these different things we're going to talk about. And it's all for you. So we want you to come in here. We want you to ask questions. We want you to learn. And we want to show live demonstrations of this stuff so you can see exactly how it's done. So feel free to reach out for other topics that you want to talk about. We encourage you to reach out to your account teams, get a hold of us in some way, shape, or form. Thank you so much for watching, and we'll see you next time on the VMware Networking and Security live stream. See ya.